Well, here we are. Happy Monday. Let's see. On Friday, we talked about Taylor polynomials, and that's sort of our motivation for going on and studying series. Our goal is to get to Taylor series, which, of course, you've already seen in Calculus 2. Part of this is we want to make it a little bit more rigorous. So there were a lot of theorems that you saw in Calc 2 that you didn't see the proof of. So for example, when it comes to Taylor series, you know that you can integrate term by term or differentiate term by term because you were told that in Calculus 2. But we're going to actually prove that you could do those things, okay? And it turns out that, what the actual term that we need there is the one we've already studied, which is uniform convergence. Okay? So, like I said, Friday we looked at Taylor polynomials. We're going to Taylor series, but today we're just going to spend today on numerical series. Okay, by numerical series I just mean a series of numbers. So there aren't going to be any functions today, unless we go a lot faster than I'm anticipating and we actually get into power series, okay? So we should define our terms, okay? We're given a sequence of real numbers. We form the series the series is just the sum of them. Okay. When it's clear, we're going to suppress that lower bound. Okay. Either when it's clear or when it really doesn't matter. And when we do that, we'll also suppress the upper bound. It'll just, in that case, it'll just be obvious we're summing to infinity. So we analyze these series by looking at their partial sums. So it's the same as you did in Calc 2. So we look at the partial sums. And partial sums also form a sequence. This one I will use the index k. I guess I could probably stand to write that. Okay. So, here's the general idea. We are very wary of these guys because that's addition going on forever. We want to be careful when we do that. But we're really happy with these guys. Yeah. Okay. Let's see if my pencil continues to give us problems. Okay, so we're happy with the partial sums. We're very wary of the infinite series. Now, it turns out that, actually, almost all of our theory is based. So you might remember back to Calc 2, you had all these nasty series that were hard to reason about. You had a billion tests. Well, I mean, it turns out that all of our theory is based on geometric series, which are the absolute easiest to analyze. Okay? So we have the identity. Oops, I should probably qualify this. If we have a real number R, we have the following identity. That's just an arithmetic identity that is always true. Okay. To see that, you just multiply through. On the left-hand side, you just expand the left-hand side. We take 1 times everything. So we would get 1 plus r squared plus r to the k. And then we'll take minus r times everything, and we'll get a minus r squared minus r to the k, and then you'll get a minus r to the k plus 1. And then there you go. Everything cancels except for 1 minus r to the k plus 1. Okay. Any questions so far? Okay. Now, you and I both know there's some convergence issues here. We haven't talked about them yet because we don't need to talk about them to talk about the partial sums. So if we make this a series, we're just going to define a sub n to be r to the n. Still, r is just any real number. Okay, then our partial sums are the partial sum sk, which is the sum that stops at the index k, would be well, the sum of those terms are really r to the n. Okay. Okay. And, oops, if maybe I'll write this in red because it's kind of important. If r is not equal to 1, we can divide by 1 minus r in our inequality above. And get 1 minus r to the k plus 1 over 1 minus r. Everybody with me so far? Are there any questions? Okay. Well, the behavior of this series is exactly the same as the behavior of this sequence of partial sums. So what can we say about the sequence of partial sums, if anyone remembers their Calc 2? You volunteers?
Well, we can talk about the limit of the sequence of partial sums, right? And that would just be our series.
Oh. Yes. Okay. Yes, so what's the limit of those partial sums?
Well, in the case of that, there are, I mean, it depends on whether r is greater, or whether or not the absolute value of r is greater than or equal to 1, right? So that's between 0 and 1, it's going to go to 1 over 1 minus r. Is that what you're asking?
Yeah, yeah.
Okay.
I realized that somehow I just inadvertently just jumped over what the definition that we have to give for series convergence. Somehow I just didn't give it. It should have gone here, right after that. So let me just write down the definition. I mean, it's what we all know. The series with the terms an converges if and only if the partial sums converge. And otherwise it diverges. Okay, so that's the partial sums are how we define the convergence of the series. And then now we can go back to where we were. We have this theorem about geometric series. Okay, from the above, we know the sequence of partial sums, and we can just kind of analyze this. If r is less than 1, r to the k plus 1 is going to go to 0. That's something we either did establish last semester or should have established last semester. If the absolute value of r is greater than 1, then r to the k plus 1 is going to go to, oops, I should be careful, more careful than that. It's just going to diverge. Okay. Our absolute value of r equal 1, we have two cases. They're both a little bit different. If r equals 1, we can't actually do this simplification of the partial sum, but we can see that the partial sum is just 1 plus 1 plus 1 plus 1. That's big. If r equals -1, then the partial sum is 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. So those partial sums are going to alternate between 0 and 1, and therefore they're going to diverge as well. Okay? So we take these, I guess there were 4 cases, we put them together in this theorem. The geometric series this thing converges if and only if the absolute value of R is less than 1. Anybody know why it's called the geometric series?
Maybe some historical reason?
Well, I mean, that's obviously the answer. Yeah, some historical reason. I don't remember myself, so I was hoping somebody might. Okay. I can give you a cute geometric proof of something. If you do the geometric series with R equal 1/2, and I want to start it at 1. What does that sum to?
1.
1. Yeah, this is the, Zeno's paradox and stuff. Here, one can make, if you do these side lengths as 1, then this is area 1/2, this is area 1/4, 1/8, 1/32. Yeah. Anyway, you can take the unit square and you can chop it up this way. So obviously the areas have to sum to 1, I guess. You can actually do that with all the geometric series. You can do a similar kind of geometric proof. I have no idea if that's where the name comes from. Okay. Please interrupt me if there are any questions. Otherwise, we are going to move on to, again, like I said, in Calc 2, you had 1,000,000 tests. There's really only one test that matters. And that might actually be a test you didn't see in Calc 2. So lots of Calc 2 classes skip the root test. I don't know, does the root test ring a bell to anybody?
I saw it.
Okay. Good. Now here's the thing, in the root test there's a limit. There really isn't a limit. The way it's done in Calc 2, there's a limit, but it really should be a limit supremum. Okay, now, limit supremum is a concept that we could have studied last semester, but we did not. Okay, so this is a little bit of an excursion or kind of a detour to fill in a gap that we have. Okay. So for the next few minutes, I'm going to talk about limit supremum. So, and let me just emphasize again, I think I said this on Friday, but for the next couple weeks, we are only thinking about real numbers and only with the standard metric. Okay. The stuff we're talking about, is kind of, it can extend to complex numbers, and it's sort of the entire basis of complex analysis. But that's kind of a whole different treatment of it than we're trying to do the real number treatment of it. Okay. So let AN be a sequence of, let's keep things simple, we'll have them be non-negative real numbers. I'm going to define a concept called the limit supremum, or the lim sup is how it's written. First, we get rid of a case. If the sequence is unbounded. Now, we've already said they're non-negative. So unbounded would mean there's no upper bound. What that means is that for any number you pick, there will be some term in the sequence that's bigger than that number. Okay, so you can pick a number, you can get a term in the sequence bigger than it. You can then pick a bigger number, get another term bigger than that. So unbounded really means there's an infinite increasing subsequence that goes off to infinity. Okay, if this sequence is unbounded, then we define the lim sup to be infinite. And this is a little bit of a break from our standard practice so far in this class. We're actually going to use the symbol infinity here as something the lim sup could equal. Okay. This is the first time we've actually done this. Okay, last semester, if you think about it, we resisted the urge to use infinity kind of as a number like this the entire course. So this is the first time we're allowing this to happen. And here in a second, we're going to divide by it, which is even better. Okay. Okay, but that's just the special case. If they're unbounded, we're going to define it to be infinite. Otherwise, which, again, that means if AN is bounded. We're going to define a sequence of suprema they're going to be denoted by alphas. And the kth term in our alpha sequence is the supremum of the a sub n starting at a sub k.
So just to make sure I'm understanding this right, does that mean that these alpha sequence is non-increasing?
Yes, perfect. That's what I was going to fish for here.
Okay.
The alpha sequence is non-increasing, exactly. And the reason it's non-increasing is that as we go farther along in the alpha sequence, we're taking the supremum of fewer and fewer numbers. So the supremum could only go down. Is that clear?
So this process here is we're just cutting like the left tail off of the sequence.
Yeah, although we never call that the tail.
The head or something like
Yeah,
that.
it might be cutting the head off, or Or we might say, we're just ignoring the initial segment.
Okay. But the point is we're removing each time just finitely many from the start?
Mhm. Yes.
Okay.
The lights went off because of the motion detector. Let me see, 1 second. I see, that must have been another change when they made these classrooms high flex. That our light switches no longer control the lights. They're controlled by motion sensors, which are only over near the door. So it's gonna be weird when we come back next fall and the lights go off because nobody came in the classroom for 20 minutes. Anyway. Right, so not only is it non-increasing, but the alphas are bounded as well, right? Because we assumed we're in the case where the ANs are bounded. So any bound on the ANs is also going to be a bound on the supremums. So we have a non-increasing bounded sequence. What can we say about that? We have a theorem about this.
The conversion.
Yes, it has a limit. And that's the limb soup. So it's the limit of the supremum of the tails. Okay? That's the limb soup. There's a limb inf as well that you can define. You'd want to go backwards. Oh, Benjamin has a question in chat. Ah. How do we know that, he asks, how do we know that the sequence of suprema is not alternating? Yeah, it's non-increasing. As we go farther along in the sequence of alphas, the supremums can only go down.
Okay, that makes sense.
The suprema is always kind of the largest element left in the sequence. I say kind of because it's a supremum, not a maximum, but it's kind of the largest element left. And the largest element left can only get smaller. Okay? So, that is our little excursion to define the limb soup. The limb soup is sort of, you take the limb soup of a sequence to get a measure of sort of how large the sequence is that can't be avoided, okay? You might have the case where like the supremum of your sequence is quite large, but that's only because of terms in the beginning. Okay, and then you say, well, the terms in the beginning don't matter, I can chop them off. So the limb soup is telling you, the largest of the terms that you actually care about. or it's the largest value that occurs infinitely often, sort of, except again, it's a supremum, not a maximum. Okay. Or another way to put it is a, result you can prove about limb soups, and actually that we're going to use here in a second. Any value larger than the limb soup will only be exceeded by finitely many of your terms. Okay? And any value smaller than the limb soup will be exceeded by infinitely many of your terms. Okay? Okay. Now, here is the root test. If you saw this in Calc 2, I'm willing to bet you didn't see it with a limb soup. You saw it with a limit. Oops. It's not at all what I want to write. Okay. Get a sequence AN. We're going to define the limb soup. Well, we're going to define capital L to be the limb soup of the nth roots of the absolute values. If L is less than 1, then the series converges. If L is greater than 1, then the series diverges. Okay. And again, if L equals 1, then the test is inconclusive. Okay. Any questions? Let's prove it. Okay. Our job would be a lot easier if we had already studied the limb soup before and established a few basic properties of it. We're sort of going to sneak those into this proof. It would also be made easier if we bothered to say, define a comparison test, which in Calc 2 you had a comparison test. If we'd actually defined that, our job would be easier too. But we're just kind of going to throw that into the proof here. Okay, so we've got a bunch of things that, we might have done as separate lemmas, but we're doing them all in this one proof. So there's a fair bit to do. Let's do first the case where L is less than 1. Now, This is standard trick when you're dealing with lim soups, or really with limits as well. You don't want to hit that number on the head. You want to go a little bit more. Okay, so we're trying to prove convergence. We want to give ourselves a little bit of room. Okay, so we're going to choose a number row so that it's between L and 1. Okay. So it's bigger than the lim soup, but it's still less than 1, and that's the important thing. Okay. Now this is what I said earlier, kind of a fact about lim soup. The lim soup here is less than rho. Okay. That means at some point the supremums had to be less than rho from then on forever. Okay? Right, so there is some point at which our sequence is always less than rho. And by our sequence, I mean the sequence we're taking the lim soup of. So not the sequence an, but the sequence absolute value an to the 1 over n. Okay, there is some capital N natural number such that the absolute value of an to the 1 over n, the nth root of that, is less than rho for all n, at least capital N. Okay? We agreed on that so far? So I'm going to write in green over here on the side kind of what we might be thinking and what might be making us optimistic about this approach. Okay, so our sequence, the sum of an is, I put in quotes, smaller than the sum of rho to the n. But I put that in quotes because it's not true. Our sequence could have sign issues going on. They could sort of only help. We have to establish that. Okay. But it is true that the sum of rho to the n does converge. Okay, because rho is a real number of absolute value less than 1. Okay? Let's look at the partial sums, because that's the only way we really have to consider a series. Okay, and now I want to say the partial sums converge, which would be the same as the series converging. And how do we show that a sequence converges?
Dr. Goddard?
Yeah.
Before we continue, are these ends related to the ends just above? Or are these completely different? Like this m is just a dummy here?
They're all dummies.
They're all dummies. Okay.
That's a dummy, 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 dummy. Yep, they're all just
Okay.
dummy variables. They're just the index variable.
Gotcha.
I should remark this M. Is this the first time? No, it's not the first time it showed up. The M is just where we start our series. That's also just doesn't matter. Okay, so how can we show that a sequence of real numbers converges if we don't have a good handle on what it actually is?
We can do a squeeze.
I guess, but we didn't actually do squeeze. I'm looking for more like a more, well, I'm looking for a general sufficient condition to show that a sequence converges. Yeah, Bolzano-Weierstrass, yeah. Yeah, well, okay, so Bolzano-Weierstrass would get us a convergent subsequence. And we want something more than that. There's a property of sequences we talk about quite a bit. And if a sequence has it, then it's guaranteed to converge. Yes, Cauchy. Let's show that the partial sums, the sequence of partial sums is Cauchy. Okay? So what do we need to do? We need to consider the difference between two partial sums. Our index variables on those partial sums, one of them I'll make k, the other I guess I'll make j. And let me just assume that those are both at least capital N. Capital N is where the row behavior takes over. Okay? Then we have sk minus sj is, now every one of the terms is going to cancel. I see. What I really want to do is put them in the right order. Let me go back to that. I want k to be greater than or equal to j. And then what's going to happen is we're going to have our sum. Well, I might as well just write it down. Okay, now all of the terms cancel except j plus 1 to k. Okay. And now I am going to move the absolute values inside. That's just our standard bound that the absolute value of a sum is at most the sum of the absolute values. Okay, now we assume that k and j are both at least capital N, so we get to use our row to the n bound on these. Okay. And now this is a geometric series, we know its sum. Okay, well row is less than 1, so we know this series converges. Right, and actually these are partial sums of a geometric series, so we know what they are. Now let's just see if I can get it right. we're looking at 1 minus rho to the k plus 1 over 1 minus rho minus 1 minus rho j plus 1 over 1 minus rho. I hope I did that correctly. Oh, I did. I absolutely did not do that correctly. That 1 shouldn't be there. It canceled. And now you see that this sequence will go to 0 as k and j. If I force both k and j to be big, these terms are going to go to 0. Okay. So in the interest of time, I'm going to leave the very end of this proof to you. Okay, to say that this actually shows that the sequence of partial sums is Cauchy. So our our series converges. And like I said, I'm going to leave it to you to show the Cauchy condition. In the other direction, we're supposed to suppose that the lim sup is greater than 1. And again, we'll choose a row. Between L and 1, although this time L is on the other side of 1. Okay. Now, if your lim sup is large, that means, so your lim sup is L, so rho is actually a little bit smaller than L. Okay. So that means that that supremum has to be bigger than rho infinitely often. Okay. Well, sorry, the supremum is not increasing. The supremum has to be bigger than rho always. But what that means about your sequence, and because of time, I'm just going to be able to write down a sketch here. This means that the sequence of which we took the lim sup must be greater than rho infinitely often. Okay, so what does that mean? That means you got a sequence, a subsequence such that for each one of those, our thing is bigger than rho. Okay. Now, if you look at the difference between the partial sums, where we had one of those big terms, and the one right before it? Well, the difference will be exactly equal to that term we just had. That'll be greater than rho to the n sub I. So our partial sums, our sequence of partial sums, is not Cauchy. Okay, and the sequence that is not Cauchy does not converge. Okay, I realize we're out of time. Let me just go back to say one quick thing. I hoped I was going to have some time for this. If that lim sup is equal to 1, we absolutely, the test does not say anything, and I will let you remember. Here's two series where that lim sup is equal to 1. One of them diverges and the other one converges. Okay, sorry for running a couple minutes over. This is basically all we're going to do with the so-called numerical series. And our next lecture, we are going to start plugging values of x in there. So we're going to start having functions. Okay, so I will see you for that on Wednesday. Have a good day.